Hello, my name is Professor Brothers, and we're going to go over an example of how to create a Bode plot. This time we're using this transfer function. H of s is equal to 100 times s plus 1 divided by s plus 10, s plus 100. This system has two poles, 1, 0, and a constant value. Before we start, let's review the steps. First thing we want to do is find the transfer function. If we look at it, we can see that the form that the transfer function is usually given in is the same form that we have. We need to do step number 2, which is putting it into the standard form. The standard form for Bode plots is a ratio between s and the polar, the 0, plus 1. After we get in that standard form, the next thing we're going to do is sketch the magnitude asymptotes, add the corrections, sum the lines, then connect the dots. We're going to repeat steps 3 through 6 for the angle plot. All right, let's get started. We have h of s is equal to 100 times s plus 1 in the numerator, divided by s plus 10, s plus 100. We want to factor out both the 10 and the 100 to get it into the standard form. So h of s is going to be equal to 100 divided by 10 times 100 times, and I'm going to write the numerator explicitly in this form, s divided by 1 plus 1. Okay? Doing it in this way will really emphasize where the omega naught value is for this 0 that's in the numerator. Divided by, in the denominator, we're going to have an s divided by 10 plus 1 and an s divided by 100 plus 1. We can continue to simplify this. We can see that we have a 100 divided by 100 gives us a 1, and a 1 divided by 10 gives us a 0.1. So this is going to be a 0.1 times s divided by 1 plus 1 divided by s divided by 10 plus 1, s divided by 100 plus 1. From this, we know the first step that we're going to do when we get to the next stage, which is plotting the asymptotes, we're going to look at this constant value and figure out what we need to put on the plot. So let's go ahead and convert that into dBs so we can plot that. This is the only thing we need to convert into dBs. So for the constant value, we can say 20 log of the absolute value of 0.1. And if we do this, we get that the constant value is going to be equal to negative 20 dBs. So we're going to remember that for the next slide. We're going to take negative 20 dBs for the constant value, and that's going to enable us to start plotting things. Okay, so now we want to actually transfer it onto the plot. We're going to start out with sketching the magnitude, the straight line asymptotes for each term. So in doing this, we're going to have an asymptote for the constant, which is at negative 20 dBs. We're going to have an asymptote for the 0, and then we're going to have an asymptote for each one of the poles. Now, we start off by saying that the constant is at negative 20. So let's go ahead and put that negative 20 onto the plot. We're going to see that we have a negative 20 going all the way across. So there's our constant value at negative 20. The next thing we can do, we can look at our 0. Because it's in the numerator, it's going to be a positive 20 dBs per decade. We can also go and look at the rules for Bode plot if we forget. So we're going to start off with a real 0. Low frequency asymptote at 0 dBs, high frequency asymptote at 20 dB per decade, and we're going to connect the asymptotes at omega naught. For the 0 in our expression, we have s divided by 1, so it's going to be connected at omega is equal to 1. So omega is equal to 1, that actually is starting right here, 10 to the 0. So we're actually starting this almost off the screen. I should have put my scale better, but we can continue beyond this because remember, this designator is not at 0. This designator, we just put it where it's convenient. So we can expand this plot and we'll just say we're going to go at 0 until we get here. And when we get here, we're going to go up at 20 dBs per decade. So 1 decade later is at from 10 to the 0, which is 1, to 10 to the 1, which is 10. And we're going to connect these two lines with a straight line. And it's going to go. So we can see we have these two different slopes. I'm going to try to make this a little straighter. We have these two slopes. We're coming in at 0. And then once the S divided by 1 term takes over and starts to dominate this term, we go up at 20 dBs per decade. So that is plotting the constant, and we're plotting the 0. Now let's go on to the first pole. The first pole is the same thing, except if we go and look at the rules, we can see that for a real, for the first pole, we're going to look at the first pole. For the pole, the only thing that changes is instead of a 20 dBs per decade, we're doing a negative 20 dBs per decade. So we're going to go out to omega of 10, which is 10 to the 1. And from here, 10 to the 1, we are going to go down at negative 20 dBs per decade. And so we've already got our negative 20 line marked with our constant. And so right here is where 1 decade later, we're going to go through there. So we're going to continue at the low frequency asymptote is 0. The high frequency asymptote is negative 20 dBs. And that goes on forever. My arrow ran off the screen. Let me put it a little higher. So that goes on forever. The final one we're going to do is another pole at 100. 100 is 10 to the squared. So that's going to actually be coming off right here. And we are going to go down at negative 20 dBs per decade because it's a pole. And so that's going to come down here and we're going to mark it right here. That's negative 20 dBs per decade. So this pole looks just like that. Now, of course, these are supposed to be straight line approximations, so please excuse me if my lines are a little bit crooked, but you get the idea. The next step, we sketch the magnitude. These are all the individual magnitude asymptotes. So we have 4 terms, our constant, our 0, pole number 1, pole number 2. We should have 4 straight line asymptotes. Here's 1, here's 2, here's 3, here's 4. Onto those, we're going to do the correction points. All of these are first order, so all these get a 3 dB correction point. Okay, so we're going to put a 3 dB correction point right here. We are going to put a 3 dB correction point right here. And we are going to put a 3 dB correction point right here. You can't see these 2 dB correction points because of the omega markings. But when we do the summation, I'll transfer them and you'll be able to see them. The next thing we do is sum the lines. When we sum these together, we look at a single frequency value and we sum all the things that are happening at that single frequency value. So I'm going to extend the constant out a little bit further so we can go a little bit to the left of the axes here. We can see when we start out all the way back here at 10 to the negative 1 type area, we're going to have a magnitude of 0 dBs plus a magnitude of negative 20. 0 plus negative 20 is negative 20. So we're going to start off and we're going to go along the negative 20 dB line. We're going to follow that line up until we get to the first inflection point. That first inflection point is this first knee that happens at omega is equal to 1. And so at omega is equal to 1, we're going to start to go in a positive 20 dB per decade. from this point. So now if you want to think about it, we are adding -20 plus these values. So we can just take this line and translate it down. And that's all we need to do. And so we're going to go until our next inflection point, which is here. And we're going to go just up like that. Now we need to transfer down this 3 dB correction point. So we're going to just say 3 dBs off this line. There's the correction point. Okay, so now we have the straight line approximation that's going up. So we are now turning on another part of it. So we have the constant, we have the 0, and we need to add in this first pole. So the +20 slope and the -20 slope sum together to give us a 0 aggregate slope. So we start right here and we can say from this point, we are going to start going at 0 dBs. And this is going to go across at 0 dBs now. I'm going to try to make this thicker so you can see it. Okay, so that's going to be 0 dBs. That is the top of our passband is what we're going to see. Now, when we finish, we want to sum in this last asymptote. So this 20 dBs and this 20 dBs are coming to a slope of 0, but now we add in a -20 dBs. We're actually on this line. So that means we are going to follow this asymptote for the finale of this summation. We need to transfer all our 3 dB points for the data corrections. So I'm going to just really emphasize this by putting an arrow and saying 3 dB correction. So there's a 3 dB correction there, and then there is a 3 dB correction that we have over here. And then we have one more 3 dB correction down here. So we have a 3 dB correction here, we have a 3 dB correction here, and we have a 3 dB correction right here. All right, so now we're going to sum all of these together, or we have summed all these together. Now we connect the dots. We go along those asymptotes and make a smooth line transition into all of these 3 dB correction points. So when we do that, what it looks like is it goes up to here and goes over to there like that. So you can see that this line is going to start out very low, -20 dBs down, and then it's going to curve up and it touches in the middle of this passband, because that's just how the 3 dB corrections are going to work. It's going to touch somewhere in this passband, or not touch, but it's going to come real close to this asymptote, and then it's going to curve back down. So it ends up going down in that manner. So let me try to make it just a little bit darker so you can see. So that is our smooth line approximation. We start out real low, and then we're going to come up here and go down like that. And so this is our filter structure. If you can see it in orange. Oh yeah, you can see it pretty good. Okay, so the orange line that's coming here is our actual magnitude response. You see that? You can tell that this is a bandpass filter. It is squashing the frequencies here, passing the frequencies here with a 0 dB gain, and then it's squashing them over here. So our filter shape comes up and comes back down, making this peak in the middle. Passband on either side of it, it's going to pass through these 3 dB correction points. That's our bandwidth. So we actually have exactly 1 decade of frequencies that we're passing. And then it continues off on both sides. All right, so let's continue on. We're going to repeat this procedure for the angle plot. So let's go back and review the rules based on the angle plot. Let's say we have a constant. If the constant is positive, we have a 0-degree phase shift. Then we have a real zero. Looking at the real zero, we have a low frequency asymptote at 0 degrees, a high frequency asymptote at positive 90. Connect them with a straight line from 1 decade below omega naught to 1 decade above omega naught. When we continue going, we see that we have 2 real poles then. These are very similar to the real zeros, except we go to negative 90, 1 decade above. All right, so let's get started with that. Let's start off with our constant. Our constant is a positive number, so that means we have a 0 degrees. Let's not even worry about that. Now we're going to go with the 0 on the numerator. And so the 0 on the numerator, I might have to expand my plot out just a little bit. So we have a 10 to the 0. So here is 1. We actually need to go 1 decade below 1. And so that's going to come out all the way to approximately here. Let's call this omega of negative 1. Omega of negative 1 is going to be out here. Omega of 0, omega of 1. And so at 1 decade below, that's where we're going to start with this top 0. And it said that we need to have an asymptote at 0 degrees. So it's going to have the asymptote along at 0. And then we're going to transition up to 90 degrees at 1 decade above. So that puts our data point right here. And that's going to be where our phase is going to go from and to. So let me see, we've got about that much for a decade. I'm a little off. Let me put omega to the negative 1 right here instead. Try and make this as straight as possible. So here is our omega of negative 1. Our asymptote goes straight along until we hit that 1 decade below value. And now we're going to connect a straight line between here and here. So something right about like in there. Okay, and that's going to go on. So that is for our first 0, or our only 0 in this example. Now we're going to go and do the same thing, except instead of going to positive 90, we're going to go to negative 90, and we're going to repeat that for 10 and for 100. So let's go at 10, 1 decade below 10, which is the value of 1. We're sitting at 0 degrees. So that's right there. We're sitting at 0 degrees. And then 1 decade above, we're sitting at 90 degrees. So 1 decade above, we're sitting at 90 degrees right there. And we want to connect these lines, these dots. And so that straight line, or somewhat straight line, let's try that again. That's not straight at all. There we go, that's better. So that straight line is for the first 0, or the first pole, excuse me. And for the second pole, it's going to be centered around 100. So 1 decade below 100, which is right here at 10 to the 1, at 10, oops, about right there, we are going to be sitting at 0. And then 1 decade above omega naught, we're going to go down to 90 degrees. And so that's right about here. And so we can see that this line is now going to look like that. So we have our straight line approximations. Again, we're not really going to worry about the corrections too much on an angle. Here's for the 0. We're going up to positive 90 degrees and then leveling off. Here's for the first pole. Here's for the second pole. So these transition points. Now we need to sum across these lines. So here at the very back end, we have 0 plus 0 plus 0. All of these result in a 0 degrees phase shift. We're going to follow that until one of these turns on, just like you were doing with the unit step functions. And we can see that we start to go up. Let me switch. I think the orange marker did pretty good to show a difference. So we're going to go at 0. How does that look? Yeah, we can see that a bit. And now we're going to transition up. This is going to go up until the second turns on. And when this second line starts to turn on, we can see that we have a positive slope and we have a negative slope. So those are going to come together in order to make a 0 slope. Now, the way this math works out, it just so happens that we're midway between a decade transition. So that means we're going to be at 45 degrees. So we're going to flatline at 45 degrees. And so we're going to come up here and we're going to go straight over on the 45-degree line. And this marker is dying. Okay, we're going to come straight over on the 45-degree line. But now something changes. This one turns off. So we're no longer canceling out this slope because this slope has went to a 0. So now we're going to start to go down in slope again. But not only did this line turn off, we picked up the interference or the actions from the other pole. So now we're not going down at 45 degrees per decade anymore. We have 2 downward slopes acting on the sum from here onwards. So we're actually going to be going at a 90 degrees per decade. We're at 45 degrees right now. So as we go forward by one more decade, we can see we're actually going to go down to negative 45 degrees on the slope. So I'm going to try to put a dot at negative 45 degrees. And so that should be pretty much between these 2 lines, right in there somewhere. And that's where we're going to end up with our straight line approximations, our straight line asymptotes. And you can see that the slope of this line is such that it actually crosses this other straight line approximation. So we are doubling the slope and therefore we're cutting through this straight line asymptote. But all these individual terms don't matter. The only thing that matters in the end is this orange line, the sum of all of the individual angles. All right, so now we have another change that happens. This slope turns off. We're no longer going at a negative 45 degrees per decade. This one is now a 0 degrees, but we still have this other pole that's influencing it at negative 45 degrees per decade. So now the slope is again going to change, but it's going to match this slope of the line immediately above it. And it is going to continue down for one more decade. And then at that point in time, this one is going to turn off. And it's going to go flat line. So now, if we add these up, if I did everything right, which I don't know if I actually got all these summed together correctly, we should be able to look at the angles that we're at here at the end and come out correct. And I don't think I am right because I think we have a 90 degrees, a negative 90 degrees, and a negative 90 degrees. So that means when I finish up with this one, it should be at negative 90 degrees. So let me look just a little bit and see what happened and what went wrong here. So we should be having the straight line approximation. It should actually cut off when it gets into here, and it should follow this one now perfectly. So my slope is a little bit dramatic on my drawing. And so this slope should actually be hitting more right here. And then when this turns off, it should follow this line out. And so this should be a harsher slope right in there, and it should not pass that, but it should actually match that asymptote when it turns off. Okay, so I'm going to try to use one more color and put the smooth line approximation in it. We can see that this line comes here and then it follows this one. And so we get the general shape of the angle. It's going to have a bump and then a little bit of an output on there. And so now if we try to put all these together and smooth the lines out, we can see that it's going to come some way in there. And this is pretty messy, but you can see the overall shape if you look more at the orange and the yellow. Straight line, levels out because these two are canceling each other out. And then we're going to start to go down dramatically. Then we're going to level off and we're going to end up being at exactly -90 degrees of phase distortion. All right. So that was all for this demonstration. The next one, we're going to do one more example on Bode plots, and this is going to be a second order plot.